Hello everyone, I hope you all are doing well. So today I'm doing a video in a different format. So I am collaborating with Abtahi
Hi.
Hai. Yeah. So we are doing 9701 October November 2018 paper 1-1 chemistry. So let's start. Okay, question number 1. The first 4 ionization energies for element X are shown in the table. So which ion of X is produced by removing an electron from a filled shell?
We need to check where there's a big jump in the ionization energies. If there's given the first, second, and third and fourth ionization energies. And in this case, we can see that there's a difference of 3000 here, 1400 here, and it's clear that this is the bigger one. So the ion must be from the fourth shell.
Yeah, because they asked which ion is produced by removing an electron from a filled shell. And so we can see that the biggest jump was between the third and fourth ionization energies. So that means the first 3 electrons were lost from the valence shell and the fourth one was lost from an inner shell, which is obviously a filled shell.
Yeah.
So yeah. Now the next question. Can we erase the annotation? Asha, you can do it. Question number 2. What is a basic assumption of the kinetic theory as applied to an ideal gas?
Collisions between gas molecules are elastic. This is right. Uh, each molecule occupies a finite volume. This is not right because an ideal gas should have zero volume, and gases consist of particles that experience the force of gravity. This is not specific to an ideal gas. Gas molecules attract each other with weak intermolecular forces. Uh, This is also not right because there should be zero intermolecular forces between ideal gas particles, right?
Yeah, because we assume that they have negligible or no volume, so then there won't be any intermolecular attractions either.
Yeah. So the only viable answer should be A.
Yeah, that's right. Because we have perfectly elastic collisions, so kinetic energy is good and all. Okay, next question. A sample of the hydrocarbon C6H12 is completely burned in dry oxygen and the product gases are collected as shown. So we have anhydrous calcium chloride, which will absorb the water from here. And then soda lime to absorb carbon dioxide. So the increases in mass of the collecting vessels P and Q are MP and MQ respectively. So what is the ratio MP over MQ?
So to begin with, we are passing hydrocarbon in dry oxygen. So let's create the equation first. C6H12. I can use text for this. Okay, so balancing X 12, 6, 18, 9. Yeah, so this is the equation for the reaction that's happening. Increasing mass of P and Q. P absorbs H2, right?
Yeah. So then MP would be the mass of the water.
Yeah.
And then MQ would be the mass of the carbon dioxide.
Mass of water here would be 6 into 18.
Yeah. Yeah, we can just take the molar mass and then so 6
Yeah.
into 18.
divided by the mass Q, which should be the mass of CO2. Because that's 6 into 12 plus 12 plus 32.
Yeah.
So I need a calculator for this.
Yeah. Already you can cancel out the 6 because both of them have the same number of moles.
Yeah, so 18 by 44.
Yeah.
Which is 0.41. So
Yeah.
the answer is A.
Yeah. Because mass is moles times the molar mass, so that's why we use this equation. So MP
Yeah.
over MP can be written this way. And yeah, that
Mm.
should be right. It's always a good way to start by writing an equation in chemistry.
Yeah.
Okay, next. 5.0 gram samples of the carbonates of barium, copper, lithium, and magnesium are decomposed to the metal oxides and carbon dioxide. For which compound is there the greatest loss in mass?
Okay, so let's make the formulas first. This is BaCO3. This is CuCO3. This is lithium carbonate, Li2CO3. And lastly, magnesium carbonate, MgCO3.
Yeah, so the first two, they're because barium and copper, like here we have copper 2 carbonates, so that's CO2 plus.
Yeah,
And the
yeah,
carbonate ion, it has a 2 minus charge, so that's why when
mm,
we make the compound we get CuCO3. For barium carbonate as well, the
yeah.
same, because it's in group 2, so it would also
And,
form Ba2 plus
and
ion.
since lithium is from group 1, it's Li plus the two of them.
Yeah, so lithium, it's in group 1, so it's going to form Li2CO3, and then magnesium again is from group 2, so it's going to form MgCO3.
Okay, so now do we calculate the moles of this? We have the relative molecular masses and the mass given in the sample. So I'm assuming we need to calculate the moles.
Yeah,
5 by what's the molar mass. Can you take out the periodic table somewhere?
yeah, I will in just a second. So now we have a periodic table, so that's good.
Okay.
Did the things get
So
yeah.
help me write the. Okay, now you can move to the periodic table. Oh, for this, 5 by lithium is 6.9. 6.9 plus carbonate is 12 plus 48, so 60 always. 60. And this barium is 137.3 plus 60. Then copper 5 by 63.5 plus 60. Magnesium carbonate by 6.9 into 2, right?
Yeah.
Magnesium carbonate Um, 5 times 24.3 plus 60.
Yeah. So 60, just if
So
you add 12 and 16 times 3, so you get
yeah,
CO3, the mass of the molar mass of it. So you can just use that in your calculation instead of doing it every time.
oh yeah, right. So here we can see that the smallest denominator should be for lithium. But what was the question again? The greatest mass increase, right?
Yeah, for which
Loss
compound
in mass.
greatest loss in mass?
So shouldn't it be C because lithium has the um, lowest denominator, which is what is it? 5 by 13.8 plus 6 is 73.8. This is the smallest among all of these, so that should produce the greatest number of moles.
Yeah,
So
this
I'm assuming it's C.
yeah, I also think it's the basically like if you're talking about the greatest loss in mass, if you write down the full equation, then like
Yeah,
Li2CO2,
this turns into
yeah,
lithium oxide, yeah,
Li2CO2.
which has the same amount of moles.
So you're losing carbon dioxide. So then the one that has the greatest moles will lose the most
Yeah, yeah.
carbon dioxide as well. And for all of them, you have a 1:1 molar ratio. I think we can check as well. So BaCO3 would give you BaO solid and carbon dioxide. But did it get erased?
It's always a 1:1 ratio. So
Yeah, BaCO3. And then for copper carbonate as well, and magnesium carbonate. So then yeah, it's an efficient way to do it if you just see which one has like the greatest number of moles, which you can see, because if the
yeah,
denominator is yeah 5, but like if you have a smaller denominator, then it's going to be bigger moles. And yeah, then it would obviously form the greatest amount of carbon dioxide as well. So it would have the greatest loss in mass. So that's for lithium carbonate because
yeah.
that has the smallest molar mass as well. So if it has the smallest molar mass, it's going to have the greatest number of moles. Okay, next question. So in this question, you should assume methane behaves as an ideal gas. The gas law can be summarized in the ideal gas equation below, PV equals to nRT. The volume of a sample of methane is measured at a temperature of 60 degrees Celsius and a pressure of 103 kilopascals. The volume measured is 5.37 into 10 to the power of minus 3 meters cubed. So what is the mass of the sample of methane given to two significant figures?
So the formula is already given, which is great, and pressure needs to be converted to pascals. 0.03 into 10 to the power 3. So now we can just input and temperature to kelvins. 60 plus 273. We're supposed to find the mass, right? Okay, so the number of moles should be pressure into volume divided by R, which is the molar gas constant, 8.31.
I think that's also in the data booklet probably. Check.
Oh,
Do they use 8.31 or 8.314?
in our syllabus, we are supposed to use 8.31.
Hmm.
We don't have a data booklet in this syllabus.
Oh, check. Maybe this is an old one. I don't know.
Yeah, it's 8.31 here.
Yeah. I've been doing a lot of ideal gas lately in university. That
Oh, oh
use
wow.
and we also have to make other
Mm-hmm.
assumptions like van der Waals
Oh,
equation, rate, and other stuff. And
I've never heard of that.
so
Anyway, so if we put in the pressure 103 into 10 to the power 3 into 5.37 into 10 to the power minus 3 divided by 8.31 into 60 plus 273. It comes off as 0.1, 0.200 rounded off. Then the mass of the sample of methane. Methane is CH4, so 12 plus 4 plus 16. And we know the usual formula. Moles equals mass by RMM, molecular formula. So MR into moles gives us the mass.
yeah,
In this case, it's 16 into 0.200. So it's 3.2. If the answer is C,
yeah, that seems like a reasonable answer, I think, as well. Now the next question. Well, this is an enthalpy change question apparently. A butane burner is used to heat water. The MR of butane is 58. The enthalpy change of combustion of butane is minus 2877 kilojoules per mole. 250 grams of water is heated from 12 degrees Celsius to 100 degrees Celsius. The burner transfers 47% of the heat released from the burning fuel to the water. You assume that the butane undergoes complete combustion and none of the water evaporates. So, what is the minimum mass of butane that must be burned?
okay, so I'm pretty sure we need the formula equals MC del T here. So del H, so divided by minus MC del T by the moles. The del HC is minus 2877, so minus 2877 I don't have a graphics tablet, so it's hard to draw using the mouse.
Oh, yeah.
Minus 2877 equals MC. C is 4.18, right?
Yeah.
Minus,
4.1.
yeah. Mass should be in kilograms, which is 0.25 kg. 0.25 into 4.18 into temperature change is 100 minus 12, which is 88.
Yeah, so in this equation, you should be using kelvins, but then because it's a temperature change, it doesn't matter if you have Celsius.
It doesn't matter, right? It gets cancelled. Yeah. Moles. It also does say that 47% of the heat released from the burning fuel to the water.
Yeah.
So Is it minus 2877 into 47%?
We could try. Let me see what the question is. So, enthalpy change of combustion of butane, the burning fuel to the water. So we don't know actually because that is the enthalpy change of combustion of butane. Yeah. We don't know the heat release, so we have to find it there.
So we have to find the heat release first.
Mm.
Oh, okay, then just this part.
Mm.
Anyway, this
It's
it
47
should be a
x.
plus 8.18 into 88. That's 91 point.
Yeah.
91.96 joules.
In the formula, by definition, we have a minus there, so this should be minus.
No, it's the minus only in the formula for the moles, this one. When we are calculating specific heat capacity using the formula, it doesn't. Like the normal formula is equals mc del T, and when we need moles, then it's minus mc del T by moles. That's according to the.
Is it, which have from what I've learned, like it depends on whether it's endothermic or
Wait,
exothermic.
you can, isn't that the syllabus in the second slide? You can check it.
I don't know, but like because we like determine whether it's endothermic or exothermic, right? So that's the use of the signs. So by definition,
Yeah, because
it should have a minus
yeah, we
because
use it for the moles.
the heat is being released, so there should be a minus sign probably. I think.
Mm. Okay, well, the calculation is the same either way. So minus 91.96.
And this is
So the energy released is minus 91.96 joules. 47% of the heat released from the burning fuel to the water is 47% into minus 91.96, which is 57.
yeah, so this is 47% of X because they said that 47% of the heat released goes to the
Yeah.
water, right? So that's why you're finding how much heat was released basically in this calculation. So 47% equals to minus 91.96.
Minus 41. Yeah. Minus 43.2 joules. Then, assuming that the butane goes under complete combustion,
How did you get minus 43.2?
47% into minus 91.96.
Why did you take this value as times 47%?
Because this is the energy released from burning the water.
No, we
Huh?
we are finding that, but then the thing is, this is the energy released. Like it's not the energy released like totally. It's the energy used to heat the water. So 47% of the total energy released is the energy used to heat the water here. We use the
Oh,
mass of
okay,
water
okay.
here, right?
Yeah.
We're finding like the energy used to heat the water. The butane burner is used to heat water, so energy used to heat water. And then
Yeah.
47% of the heat release totally was used to heat the water. So this equals to 47% of the heat release. So we have to modify that.
47% into x equals 91.96. Or x should be 91.96 by 47%.
1.96 by 0.47. So
which is 195.66 joules. Then isn't it kilojoules? 195.6 kilojoules. Yeah.
yes, because over here we used, I think,
Yeah,
it should be in kilojoules.
minus 195.6 kilojoules. Then I think we need the equation.
Over here, because we use this value, right? We use the mass of water in kilograms, and then we use this before, say, 4.18 kilojoules per kilogram per Kelvin. So then kilojoules would be a unit, yeah.
We need the equation for this against butane, so C4H10, it's being combusted plus O2 plus CO2 plus H2O. There's 4 carbons, 5 hydrogen waters, and 5 and 8, 13 by 2. Now it's being combusted, and we found out the enthalpy change of what, water? We know this as minus 2877.
Yeah, so we know that. So we basically know that, like, over here, what is the minimum mass of butane that must be burned? That's the question, right? And for the enthalpy change of combustion of butane, that's defined for 1 mole of butane, right? So what will be the MR of 1 mole of butane, the molar mass? That's going to be 4 times 12 plus 10 times 1.
58.
Yeah, so that's 58 grams per mole. So what is the minimum mass of butane that must be burned? So we know that the enthalpy change of combustion of butane is minus 2877. That means if we have 58 grams, right, then we have minus 2877 kilojoules of energy released, because we use this fact, right? And then what's the minimum mass of the butane that must be burned? Here we got, from this calculation, we got that if we get this much energy, if we're heating the water using this much energy, and that's 49% of the total heat released. Over here we got X as minus 195.6. So that means, yeah, this is minus 195.6 kilojoules. So then how much energy would we need for that, right? So that's what we have to find out.
So since 58, we can apply unitary method here, right?
Yeah. And we can
So 1 gram is minus 2877 by 58. So minus 49.6. And Mg is 195.6 divided by minus 49.6. You get 3.94 from this. So the answer is C, right?
Yeah, I guess that seems right. So yeah, you can yeah do it that way as well. Like 1 gram is 277 by 50 is 49.6, and then 195.6 divided by that. Or you could just cross multiply, so x equals 58 times 195 divided by 277. So yeah, you get the answer as C, so that should be right. Okay, next question now. Wait, I can't scroll. Okay, guys, we're back. So, question number 7. Nitric acid is known to take part in the oxidation of atmospheric sulfur dioxide. One possible reaction is shown. So, this is SO2 plus HNO3 giving you NO plus and HSO4 minus. So, which row shows the correct changes in oxidation numbers of nitrogen and sulfur?
Okay, so we can see that sulfur and nitrogen here. Here is oxygen is always O2 minus unless in hydrogen peroxide or peroxides in general. So it's 4 minus and yes 4 plus. Here HNO3 again oxygen should be 2 minus into 3 into 3. So 6 minus, and then hydrogen should be plus 1. Again, hydrogen is always plus 1 unless in metal hydrides. So plus 1 minus 6, and nitrogen is then plus 5. So N 5 plus. And here it's O2 minus, and you can see that it's a positive ion, so N must be 3 plus. And HSO4 minus, oxygen is 8 minus, hydrogen is 1 plus 1. So S should be plus 7. No, wait, it's a negative ion, so plus 6. So S plus 6 plus. Change is for sulfur, it's plus 2 change. And for nitrogen, it's a minus 2 change. So the answer should be B.
Yeah. So basically, we're using the logic that for like a compound, the overall oxidation state will be 0. So then you can, because
Yeah,
hydrogen is plus 5, then we take this as x, then plus minus 6, because one oxygen is minus 2. Like oxygen will always have minus 2, but then because you have 3, so you can kind of, in your calculations, you can multiply that by 3, although obviously oxygen will just have minus 2, but then because you have 3, so you multiply that by 3. And so that equals to 0. And for the ions, yeah, because it's plus, so then the overall charge will be plus. So we use that in our calculations and so on. So yeah, we get the answer as B. Okay, next question now. I don't know why the screen keeps shrinking. Wait a second. The Zoom is annoying. I just found out that apparently
yeah.
you can't join meetings immediately after one meeting is finished. Okay, let's clear this up. A transition metal ion M2 plus reacts with acidified dichromate 6 ions to form M4 plus ions, Cr3 plus ions, and H2O. So which equation correctly represents this reaction?
Transition metal is being oxidized as it gains loses 2 electrons. Okay. So Cr2 minus Cr2O7 2 minus is being reduced to Cr3 plus ions. Considering here it's minus 14 and plus 6 into 2. So now first we need to balance the atoms. So we are allowed to add water to the side. We need 7 oxygens, so 7H2.
Yeah, so water can be used to balance oxygen, so you can add.
Yeah, 7H2O. Now to balance the hydrogens here, we need to add 14H plus. And here should be 2. That should be the balanced equation for the half equation of chromium. For the other equation, we have M2 plus. Oh, wait, the electrons. Right?
Yeah, we have to see whether the charges on both sides are equal. So we balance the electrons.
There's 14 plus here, 2 minus, 12 plus overall charge. And here it's 6 plus. So we can either negate 6 electrons from here or add 6 electrons here. I'm going to remove 6 electrons from the right side. Minus 6E minus. Okay, so then M2 plus is being oxidized to M4 plus, where 2 electrons are being lost, so minus 2E minus. Next, we need to balance the number of electrons, so into 3 is 3M2 plus minus 6E minus 3M4 plus. Now, if we add these 2 equations, like we can add this one to this one, the electrons get cancelled out, and we have 14H plus 1 Cr2O7 minus plus 3M2 plus 2 Cr3 plus 7H2O and 3M plus. The answer should be C.
Yeah, so what we got from our calculations, yeah, that's C. Also, you could either subtract the electrons or you could make it plus 6E minus
Yeah.
1 plus 6E minus, as long as they cancel out. So they have to cancel out, so
Yeah.
multiplied by 3 here. But yeah, and so just remember that, like, if you have Cr2O7, so over here oxygen you can balance using water, and then the hydrogen you can balance using H plus, and then you have to see if the charges are canceling out. So you, according to how much, like what charge you have here, what charge you have here, you add the appropriate number of electrons and do the same thing for the one here, but then we don't have oxygen or hydrogen here, so it's more simpler. Okay, next question. So question number 9. In this question, you should assume that all gases behave ideally. So yeah, we can probably apply PV equals NRT. That depends on what the question is, I suppose. Hydrogen and iodine react reversibly in the following reaction. Okay, it's a reversible reaction. The system reaches dynamic equilibrium. So which statement must be true for the Kp of this equilibrium to be constant? Okay. So let's see the question.
KP, the partial pressures of H2I2 and HI are equal. I think you should know that KP is only affected by temperature.
Yeah, so in general, yeah, equilibrium constants are only affected by temperature.
Yeah, so partial pressure wouldn't really affect it. External pressure also won't affect the KP. Forward and reverse reactions have stopped. This would stop the reaction, I'm assuming, because that's not even dynamic equilibrium. The reactions always continue. The temperature is constant. Yeah, I think it's T because Kp is constant when temperature is constant.
Yeah, it should be D. So even if you read the question, so if we write down the expression for Kp, so that's Kp, so we first write the product, so there we have the partial pressure of Hi squared because we have two moles, the stoichiometric coefficient is 2, and then for the reactants, those will be in the denominator, so we have the partial pressure of hydrogen times the partial pressure of iodine. And so the partial pressures of H2, I2, and Hi are equal. I mean, that's not really necessary, obviously. And the external pressure is constant. Again, even if like the external pressure was not constant, like we would still reach equilibrium. So for example, by the way, I will go back here and I realized my mistake in
Uh,
my explanation. So Kp equals to P square Hi divided by pH2 times Pi2. So for example, if we increase the pressure, right? So then, well, firstly, we have the same number of moles here. So we have 2 moles here and 2 moles here. So there should be no change because if we have the same number of moles, then the pressure will be the same if you increase it or decrease it, right? So you're not going to have any change in Kp just by changing the pressure because pressure represents the number of moles of gas in a certain volume, right? So that's why, because basically concentration is moles by volume, and so pressure is kind of analogous to that, but in a gas setting. And so that's reason because we have 2 moles here, 2 moles here, but then even if we don't consider that, like basically if we increase the pressure, we are increasing the number of moles of gas. So then here we would have an increase, but then to counteract that, equilibrium will shift to the left hand side. So this will also increase. So if this increases and this increases, we have an increase in the numerator and an increase in the denominator. So then overall Kp remains the same. But then for temperature, because this is exo and this is endo, I'll choose a different color to write this, but this is an exothermic reaction because we have a negative delta H. Here we have an endothermic reaction. So then if we, for example, decrease the temperature, that will favor the forward reaction. So if we're changing the temperature, we're not really affecting the number of moles, right? But pressure, by definition, we were increasing these moles, and so equilibrium tried to shift it here to increase the reactants moles as well. And so our expressions remain the same. But then here, if we decrease the temperature, then the reaction is counteracting that by shifting to the right hand side because the forward reaction is exothermic. So here we have a decrease, here we have an increase. So then if that decreases, that increases, then Kp will change. Does that make sense? Okay. 0.200 moles of sulfur dioxide and 0.200 moles of oxygen are placed in a 1 cubic decimeter sealed container. The gases are allowed to react until equilibrium is reached. 2SO2 plus O2 gives 2SO3. At equilibrium, there is 0.100 moles of SO3 in the container. So what is the value of Kc?
Okay, so firstly we can write down the initial moles, initial and final moles. SO2, O2. SO3. Okay, so the initial moles are 0.2 moles of sulfur dioxide, 0.2 moles of oxygen, and nothing is given for sulfur trioxide, so we can assume it as 0.
Yeah.
For the final moles, there is 0.1 mole of SO3, 0.1. And since, okay, so if 0.1 mole is added to this side of the reaction, then it has to be subtracted from this side of the reaction. And this depends on molar ratio, since it's 1:2 here, oxygen to SO3. So it's divided by 2, like 0.2 minus 0.1 by 2. And here the molar ratio is equal, so 0.2 minus 0.1. And we can get 0.1 here and 0.15 here. Yeah, then the formula for Kc is SO3, concentration of SO3 squared divided by concentration of SO2 squared into concentration of oxygen.
Yeah.
This square is because of the number of moles, by the way. Anyway, then we can place the values of final moles. SO3 is 0.1 square. Oh, by the way, we are considering the moles instead of concentration here because 1 mole per dm cube gets cancelled either way, so it doesn't matter. Both normally you would need to find the concentration in the moles, like 0.2 by 1 is equal to 0.2 mole per dm cube. So here 0.1 squared by SO2 is 0.1 square, which gets cancelled out into 0.15. Cancel, cancel. Get 1 by 0.15. That's 6.67. So the answer is D.
Yeah. And then also you can, if you look at the units, you can immediately cancel out A and B anyways, because your concentrations will be in moles per cubic decimeter. So
All right, yeah.
you have
Units.
squared, and then you divide that by moles per cubic decimeter squared for SO2 squared, and then O2, that's also moles per cubic decimeter. And so those two get cancelled, and so you get 1 over moles per cubic decimeter, so that becomes mole minus 1 dm cubed. Yeah, so we can immediately get those two out. If you calculate the calculation, you get D. So yeah. Also, let's just clear this with. Yeah, okay. And now we go to the next question. Question number 11. The two reactions are shown. Reaction 1, N2 plus 3H2 giving 2NH3, and then reaction 2 is 2O3, which is ozone, giving you 3O2. So in reaction 1, a finely powdered iron catalyst is used. In reaction 2, a vaporized tetrachloromethane catalyst in ultraviolet light is used. So which statement about the catalysts used is correct?
So both reaction 1 and 2 use a, wait, let me check the catalyst. Finely powdered iron catalyst, which is a solid catalyst, and the next is tetrachloromethane vaporized. This shows that this is a gaseous catalyst. Okay, so in this reaction 2, we use a gaseous catalyst with gaseous reactants and products. So This is a homogeneous catalyst. And in this case, we use a solid catalyst with gaseous reactants and products. So that's a heterogeneous catalyst. So, okay. So both reaction 1 and 2 use a heterogeneous catalyst. This is wrong. Both reaction 1 and 2 use a homogeneous catalyst. This is also wrong. Reaction 1 uses a heterogeneous catalyst and reaction 2 uses a homogeneous catalyst. This is right. Wrong. So the answer should be C.
Yeah, it makes sense because heterogeneous catalyst means that the catalyst is in a different state from the reactants, and then homogeneous means it's in the same state. So if they said vaporized, that means it's gaseous. So then, yeah, it's in the same state as ozone, and then heterogeneous iron catalyst is solid, whereas these two are gaseous. So yeah, that makes sense. And now we will go to the next question. So sodium and sulfur are burned separately in oxygen. Each reaction has a distinctive colored flame. So which row is correct?
Okay, so sodium and sulfur bind. Sodium usually burns in an yellow colored flame. And sulfur also burns in a blue colored flame. White won't be viable for sodium since white is only for magnesium and aluminum. So A and B are crossed. And sulfur burns in blue. So the only answer should be C.
Yeah, so that's just about the flame test, and yeah, you have to kind of
Yeah,
know the colors or have seen.
memorize it.
But yeah, so that's yellow and that's blue. Now we go to the next question. Okay, so X and Y are elements in period 3 of the periodic table. The oxide of X is solid at room temperature. This oxide has a giant structure. The chloride of X does not react with water, and argon is the only element in period 3 with a lower melting point than Y. So what could be the formula of a compound formed between elements X and Y? So I guess we can also just write down the third period so it's clear to see. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay, so we can
Yep.
look at the
So the only oxide with a giant structure should be the one in the fourth group, and which is silicon, the fourth group. So silicon dioxide is a giant structure, SiO2. Then the chloride of X does not react with water. The chloride that does not react with water which one is it again?
I think it might be easier to start by saying that argon is the only element in period 3 with a lower melting point than Y. So we can
Oh,
draw the graph, right? So we have firstly sodium, then because
and
sodium,
then
magnesium,
Mg.
aluminum, yeah, they're all metals, then Na plus would,
Yeah.
then Mg 2 plus because it's losing 2 electrons, so it has a greater C of electrons. And so
Mm,
they have a stronger metallic bonding. So these three have metallic bonding. Silicon, because it's a giant structure, it has the highest melting point. And yeah, actually I'm making uh, a difference in the diagram you drew, although it's correct,
mm,
but then you should clearly show that these all are lower than sodium because they're non-metals, right? So phosphorus
yeah,
exists as P4, and then sulfur exists as S8, so it's going to have a higher melting point than phosphorus. Chlorine exists as Cl2, so it's going to have a lower melting point than these two. And then argon, because it's just a noble gas, so it's going to have the lowest, right? So yeah, we should write it like that kind of. See, yeah, that should be fine. See a bit lower.
Yeah.
I hope you guys get it. But then we can see that, okay, so which element here has, so argon is the only element in period 3 with a lower melting point than Y. So then what would Y be? Yeah.
Argon is the only melting point with low impurity with the lower melting point than Y. So Y should be Cl. Yeah.
So it's going to be Cl. That means we can cancel out A and B because they don't have chlorine.
Yeah.
So that means it's either C or D. So at least we can narrow it down to that.
Wait, does one do nothing? Isn't that SiO2? Like the first point, does it have no significance?
Al2S3. That's not SiO2 because that's sulfur. So yeah.
Oh.
But then yeah, I mean we already
Which
canceled.
other oxide has a giant structure other than a SiO2?
Well, we could have NaO2 or Na2O, sorry. Could have that. That would be
Oh,
giant because it's ionic, right?
yeah,
So
yeah. Oh, right.
yeah,
Sorry,
so
I thought it
and
was a giant covalent structure. Like that.
yeah, this just said giant, they didn't say giant ionic
Yeah,
or
yeah. It
covalent.
can be ionic as well.
Yeah,
Okay, so the only one with PCl5 is not a giant structure, it's a simple molecular structure. So the only option should be C, since giant means ionic as well.
yeah. Because then the oxide like of X, so we have Y, we already said it's chlorine, and then X we
Hmm.
assume sodium. So then yeah, it's a solid because it is ionic at room, or like at room temperature, it will be then solid. And then the chloride of X does not react with water. Yeah, that's right, because
Yeah,
NaCl, again, it's ionic. So then in water it won't really react, it will just
it just
uh,
ionizes.
yeah, just dissolve. So then you get NaCl aqueous,
Yeah,
or say it like that. But then I mean, we already canceled out A and B, but then if you look at D, PCl5, yeah, PCl5, firstly, it's not a solid room temperature. Actually, it is a solid at room temperature. Never mind. PCl5, because, yeah, that's PCl5. It will be a solid. Why it's solid. And PCl3 would be the liquid, right? Yeah, colorless.
yeah.
And I mean, you could write a reaction for PCl5. So PCl5 plus H2O gives you POCl3 plus HCl, and then you could balance that. So 2HCl, or another
Hmm.
reaction you could write actually is PCl5 plus 4H2O. I think you could write that, right? Yeah, so you get H3PO4 then plus 5HCl. Yeah, that should be that balanced. So you would have those two equations. So then PCl5, it does react with water, right? So we can also cancel it out for that reason. So yeah, C is going to be the answer then.
Yep.
Clear, all rows with it. Now we're in the next question. Which row describes the structure and bonding of SiO2 and SiCl4?
Okay, so SiO2 is covalent and it's a giant covalent structure since Si is in group 4. So we can cancel out these two. Giant covalent. And SiCl4 is a covalent structure, but it's not giant. Si, the simple molecular structure. Something like this. So I think it's B.
Yeah, yeah, it should be right. So SiO2, yeah, it will be giant covalent, whereas SiCl4 is simple covalent. And now the next question. A sample of anhydrous calcium nitrate is placed in a test tube and heated in a roaring Bunsen flame until it decomposes. Description of the gas in the test tube is then noted. A glowing splint is then put into the test tube and any changes are noted. So it's a glowing splint, so that means they're doing the test for oxygen, right? Because a
Yeah.
glowing splint will relight, confirming the presence of oxygen.
Mm.
Yeah, so they're decomposing calcium nitrate. So what would be the equation for that? We should probably write that down.
CaO plus NO2 plus half O2. Here's the equation if I'm not wrong.
Yeah, and there should also be a two there because we have.
All right.
Yeah.
Yeah.
Yeah. So
Okay.
we can write down.
The glowing spleen goes, this is wrong. Oxygen test, glowing spleen realize. It's either B or D. Description of the gas in the test tube. We know nitrogen dioxide is a brown gas, not colorless. So the only option should be B.
Yeah, because nitrogen gas is brown and also oxygen gas, because the test for oxygen gas is that a glowing spleen
Yeah.
relights. So then these two should be right, or these two. So then we get B as the answer. Yeah, that should be right. Okay. Next question. Which row correctly describes the properties of the halogens as group 17 is descended from chlorine to iodine? You can write it down actually. Firstly, I guess fluorine,
Yeah. Group
chlorine.
7.
I'm writing them like how they exist is so
Down the group. Yeah.
iodine. We usually ignore astatine, so maybe we don't need to write it, I guess. But
Which properties of the halogens is as descended from chlorine to iodine? Okay. So down the group, the atomic radius increases. Okay, that doesn't matter here, but anyway, down the group, they have higher melting and boiling points. Iodine is a solid at RTP. So volatility decreases. Volatility is the ability of an a compound to turn into gas. Yeah, something like that.
yeah,
So volatility decreases. C and D are wrong. Strength as an oxidizing agent. This also decreases down the group. As we know, fluorine is the most reactive in group 17. So the strength as an oxidizing agent decreases down the group. So the answer should be A.
yeah. So that's right. Because they're all non-polar covalent compounds, right? Because it's just FFClCl, so all of these bonds are non-polar. So that means your strongest intermolecular forces will be just your temporary dipole induced dipole forces. Yeah.
Yeah, which
Oh.
scales with the number of electrons.
Yeah, so that it increases as your number of electrons increase, or technically if your number of electrons increase, that also means if your molar mass increases, so then down the group, yeah, again you're getting mm, a greater molar mass, you're getting greater number of electrons, so then that means your temporary dipole induced dipole forces will be stronger, which means it's harder, the volatility will then decrease, because yeah, that's why again this is gaseous and then liquid, solid, because your volatility decreases. And then yeah, strength as oxidizing agent, fluorine, you have F2, that will have an oxidation state of 0. Then you have fluoride ion, which has -1. From 0 to -1, you're you're decreasing in oxidation state, right? So that is reduction. So if fluorine is being reduced to fluoride, that means that it is an oxidizing agent, right? So all of these are oxidizing agents. And then yeah, as you go down the group, your strength as oxidizing agent will um, decrease.
Yeah.
So now we can go to the next question.
Wait, there's 1 minute left for the meeting.
Oh yeah, let me just say one thing that like um yeah, there's strength as oxidizing agent decreases because like if you have a bigger atom, then it's harder to gain electrons, right? There's less nuclear force of attraction, so that's why it'll be harder for iodine to gain electrons compared to fluorine, which has the valence shell is much nearer to the nucleus, so it's easier for fluorine to gain electrons in reduction than it is for iodine. So that's why the strength as oxidizing agent decreases. So yeah, A is going to be the answer, and we'll start a new meeting then.
Yeah.
Okay, question number 17 now. Reaction 1. Chlorine reacts with cold aqueous sodium hydroxide to form solution Z. Reaction 2. Solution Z is heated and forms ClO3 minus and Cl minus. So which equations represent reaction 1 and reaction 2?
Okay, first reaction, so chlorine reacting with cold sodium hydroxide, cold. This forms NaCl plus NaClO plus H2O, right?
Yeah.
And then this balanced no, yeah, now it should be balanced. Yep. So since this is a reaction for the first one, and the second reaction, solution Z is heated and it forms ClO3 minus and Cl minus. Solution Z is this part of the reaction NaCl, this part. Okay, so for reaction 1, let me form the ionic equation Cl2 plus 2Na plus 2OH minus forms Na plus Cl minus 2 actually, since there's 2 of them, plus O2 minus. Okay, and H2O stays as it is because it's a liquid. The rest are aqueous. And these get cancelled. So left is Cl2 plus 2OH minus 2. Oh wait, this does not get broken down. ClO minus plus 2 ClO minus. Wait, 1 ClO minus. Okay, so Cl2 plus 2OH minus. So it's either C or D.
Yeah.
Then for reaction 2, we have 2 ClO minus. Okay, 2 ClO minus plus H2. This is heated. To form I'm not sure about this. What happens when ClO3 minus is, oh right, this given, never mind. ClO3 minus plus Cl minus. So to balance this, we can get, is it 3 ClO minus?
It Could be. Maybe we can, because water is just the solvent, right? So maybe we could, like OH minus as well. So we could just write it as ClO minus, giving you
Mm.
ClO3 minus and Cl minus.
Okay.
And
Yeah.
then what we could, like, that's just the thing we start with. Obviously, it's not balanced.
Yeah.
But yeah, we could
To
then,
balance the oxygen. See.
yeah, we could think of it as like a disproportionation reaction.
Mm.
So it's like ClO minus is being reduced and is being oxidized at the same time. So we could think of it as
Yeah.
minus going to ClO3 minus, ClO minus going to Cl minus. Do you want to try it now?
Yeah. Then that's a simple balancing, right? Since there is three oxygen here, and three, and to balance the chlorine two here. So it should be D.
Yeah, that's valid. Or you could use the electron method as well.
Yeah. It's easier with the atom method, but yeah, electron method is viable as well.
Yeah, so you just make this plus 2H2O, and then because over here you have, yeah, okay, so minus 1, and okay, so here we need also plus H2O. Yeah, I guess it might be easier that way, yeah. But yeah,
Mm.
we can go to the next question. So we have the answer was D. Which statement explains the observation that magnesium hydroxide dissolves in aqueous ammonium chloride but not in aqueous sodium chloride?
So magnesium hydroxide dissolves in aqueous ammonium chloride in H4Cl, but not in aqueous sodium chloride. The ionic radius of the NH4 plus, wait, sorry, the ionic radius of NH4 plus ion is similar to that of Mg2 plus and that of Na plus. Uh, I don't think this is the answer. It's not similar, is it?
I mean, it doesn't really explain that observation either, that magnesium
Yeah,
hydroxide dissolves in aqueous ammonium chloride, not in
yeah.
aqueous sodium chloride. Doesn't really relate that much.
Mhm. Next, NH4Cl dissociates less fully than NaCl. That NH4Cl does not dissociate less fully than NaCl, right? And I don't think, again, that explains this observation either.
Yeah. I mean, NaCl, yeah, it will dissociate more, I think. But yeah, anyway,
Yeah.
then we can't really again explain that using that.
Mhm. Next is Na plus and Mg2 plus have the same number of electrons. Uh, that's true, but I don't think that explains this observation because number of electrons being same won't really make magnesium hydroxide dissolve in it. Yeah, this is completely wrong as an observation. And lastly, NH4 plus ion can donate a proton. Yeah, right. That's the only option left anyway. So it's D. And NH4 plus ion can donate a proton since it can it has a positive uh, wait, this is the structure for NH4 plus. Bad drawing, but yeah, it's something like that. And Na plus is just a metal. It can't donate a proton like this can donate a hydrogen. Yeah, I think that's why it should be D.
Yeah, because yeah, magnesium hydroxide, that's a base. Wait, sorry. That's a base. And then so it will dissolve in NH4Cl, which is acidic, right? Because NH3 is basic.
Yeah.
And so NH4Cl will be acidic. But then yeah, NaCl, that's just neutral. It's not really going to dissolve.
Yeah, right.
So the option that makes the most sense, yeah, then it's going to be D. NH4 plus ion can donate a proton that is because it's acidic, and so it will react with, like, it will, yeah, dissolve magnesium hydroxide. So we can, well, in this case, I guess, but when they dissolve, then I guess they do mean kind of reaction, but yeah. Question number 19. Transition elements and their compounds are widely used as catalysts. What is the identity and what is the oxidation number of the element present in the catalyst used in the contact process?
Contact process is the general equation is contact process is used to contact process is used to turn to make sulfuric acid. Sorry, I was forwarded for a second. So the basic equation for this where a catalyst is needed. Here you need vanadium 5 oxide as a catalyst.
Yes, this is equilibrium. But yeah, it's vanadium dioxide.
Yeah. So it's not iron, and vanadium oxidation number is +5, is V2O5. Oxygen is 10 minus and 2N25 plus. Yeah, so it should be D.
Yeah. So yeah, for the contact process, we have vanadium pentoxide as the catalyst. Or what's happening? And this step in the reaction is an equilibrium. But yeah, and then if they're talking about iron, then that's for the Haber process, which is for the manufacture of ammonia. So that's different. And now we can go to the next question. So what is true of every nucleophile?
What is true of every nucleophile? Firstly, a nucleophile is an electron-rich species. So it donates electrons. It attacks a double bond, donates a lone pair of electrons. It attacks a double bond. Do nucleophiles attack a double bond?
Well,
No, they attack a single bond, right? Like the electrophiles. Yeah. You know, it's
yeah,
the nucleophilic reactions are usually like something like this. Double bonds are attacked only by electrophiles. Plus, and this is a new, let's say, a nucleophile like CN minus. It would donate the lone pair to this electrophile pair. So I don't think it attacks a double bond. It donates a lone pair of electrons. Yeah, that's true in any nucleophilic addition or nucleophilic substitution. It does donate a lone pair of electron. For example, here carbon lone pair is being donated to the electrophile. It should be B, and but let's check the other options too. There's a single atom, not necessarily, and it is negatively charged. Uh, that's that makes a point, but are all nucleophiles negatively charged?
Well, I mean, first you have OH minus, so that could be negatively charged, but then you could also have water as a nucleophile, right? Water is a
Yeah,
water is a nucleophile because it has a lone pair of electrons.
right.
I mean, the
Yeah,
important thing
yeah.
is to have a lone pair of electrons, so it's not
Hmm.
necessary that every nucleophile is negatively charged. Yeah, water is a weaker
Yeah.
nucleophile, but it's still a nucleophile, so
Mm-hmm.
that's the thing.
Yeah, so it should be B.
Yeah. And yeah, it's true that like I mean, why would a nucleophile attack a double bond? In general, it wouldn't do that because a double bond is already a region of high electron density, right?
Yeah, yeah.
And therefore, an electrophile would be attracted to that region of high electron
Mm-hmm.
density. But then, if you have a nucleophile which is already electron rich, it wouldn't really be attracted to that region. But then, this partially positive carbon, it would want to attack it, right? So yeah,
Yeah.
and yeah, so the answer is going to be B.
Mm.
Just should we stop here or?
Yeah,
Uh,
we can continue on the next one.
yeah, okay. Do you want to do the next one or we will do it later? Okay.
We can do it later.
Okay, so let's do question number 21 now. X has the molecular formula C5H12O. X has a branched carbon skeleton and a secondary alcohol functional group. So how many structural isomers fit this description of X?
So, uh, X is the if I write it like this, if I write another noise, it's easy to understand that X would be an alcohol stated, and say that it's a secondary alcohol. So, draw the pre-split formula. It will be easier. For it to be a secondary alcohol, it has to be somewhere either here or here. I mean the OH group, or yeah, here. Assuming the OH group to be here, we can identify that there are three structural isomers, like one, then here, here. That should be three. So
Yeah,
I
but
think the
then
answer is C.
you also mentioned another criteria that the carbon skeleton is branched, right?
Uh,
As
oh,
well.
right.
Yeah.
The branched carbon skeleton. So other, firstly, will be branched, so probably a methyl group here. The methyl group can also be here, and the OH can be here, 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 or here. So now that we have two methyl groups, one possibility is that a methyl group here and two an OH here or here, and another possibility should be this methyl group here Oh wait, that's the same.
Yeah, it would be the same.
Yeah. Or should it be two? There's just two possible places for the wage group to be.
Yeah, I mean, if you draw like, oh, look at this annotation thing changed. Okay. So, yeah, we could have a four carbon chain and then one methyl group in on like the second position. So if you like just label it one, two, three, four, in either in any direction. So even if you go in the opposite direction, it's fine. Either carbon two or three. But then because it's a secondary alcohol functional group, so we can't have the OH here, right? Then because
Oh right,
secondary,
right.
yeah, this would be,
That's tertiary.
yeah, that would have like three carbons attached. This
Mhm.
OH would have three carbons attached to this carbon atom. So
Yeah,
that to me it's tertiary. So we can't have it there. The only position possible is this one because then it would be secondary, right?
yeah.
Yeah, so that's one possible position. And then if we had three carbon atoms and then like two methyl groups, then yeah, obviously then you can't have
Well, no
secondary alcohol.
possibility, right? Because it's all primary.
Yeah, so we would only have a primary alcohol because you can't attach an OH here. Because carbon can only
So
form four bonds.
ignoring this one should just be one.
Yeah, so it should just be one
Yeah.
structured isomer then.
Mm.
And yeah, the next question. A new jet fuel has been produced that is a mixture of different structural isomers of compound Q. Which structural formula represents a structural isomer of Q? Okay.
Local formula represents structure isomer. Okay. So structure isomer should have branch and the same number of carbon and hydrogen atoms. Okay, so for Q, it has these one, two, three, four, five.
So you're just drawing Q right now, like in
Yeah,
displayed
I'm
form.
drawing Q. Yeah. It has 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbon.
Yeah, one, two, three.
And it should, there are no double bonds, so I'm assuming it's an alkane. So C14, 8, 30. Okay. And now I can check for the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is this possible? 3, 4, 5, 6, 7, 9, 10, 11, 12,
Yeah, this one
13.
also has 14 carbon atoms then.
Yeah, it's possible.
Hmm.
This has 13.
Yeah, so then
Yeah,
that
so
would
it's not.
immediately be.
Yeah, this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is also possible. 14. And 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13. default. Yeah, this is also possible.
Yeah. So we've eliminated B at least.
Yeah. Now, a structure isomer. Uh,
We can look at how long the parent chain is in each of them and like which positions the substituents are at. So it's good if we label it, maybe like we could just label the carbon chain like from either side. I think it's symmetrical, right? So it's fine. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the parent chain is 9 carbon atoms long. And then you have substituents at position 2, 3, 5, 7, and 8, right? So yeah, we just look at A, C, and D and see which one is different than this. So like it still has 14 carbon atoms, but then yeah. So like A, we could start from either end. Yeah.
2, 3, 4, 5, 6, 7, 8. We have the
That you
at
the parent
7.
chain will be the longest one, right? So you would not go here, you would actually go down here. So 8
Oh,
and 9 because you have to take the longest possible chain.
oh,
That's the thing. But yeah, now we just see the substituents.
yeah, so firstly, there is one at 8 and one at 7. Then one at 5, 3, and 2. This is not an isomer because there's one extra at 8.
It's literally the same as that one. Like 1, 3, 5, 7, 8. 1, 3, 5, 7, 8. So it's literally the same compound then, not an isomer.
And for the next one,
You can cancel that. Yeah.
1, 2, 3, 4, 5, 6, 7.
Yeah, so that could be a possibility then.
1 at 6, 1 at 5, 3, and 4. This is a nice one probably.
Yeah, yeah, it's possible because it has
I think
like a
C is the
different
answer.
length
Yeah.
of the parent chain and also like the
But let
substituents.
me check D as well. Just
Yeah,
for yeah, sure. 1, 2, 3, 4, 5, 6, 7, 8.
yeah. Again, we could start from because we always want to take the longest carbon chain, right? So instead of starting from here, we would start from something like that.
Okay. Messing it up.
Uh,
1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's the same here as well. 8, 7, 5, 2, and 3. So yeah, it's the same as the one like our original cube. It's
yeah, it's
not an
also
isomer.
same.
Yeah.
So then yeah, we cancelled B because it had a different number of carbon atoms, and A and D were the same compound, so that was useless. But then C, it was the only one which had like a different length of the parent chain and then different substituents, like the order of the substituents was different. So yeah, but then it had the same number of carbon atoms, so it's an isomer. Yeah, let's go to the next question now. Okay, question 23. The conversion of propene to propane 2 can be carried out in two stages represented by the equations shown. So CH3, CH double bond CH2 plus HI, giving you CH3, CHI, CH3. And then you have CH3, CHI, CH3 plus KOH, giving you CH3, CHOH, CH3 plus K plus I minus. So how can these two reactions be described?
Okay, so the first reaction shows um, hydrogen iodide being added to an alkene by addition, since there's only one product, and the double bond breaks so to form an electrophile of the carbocation. So yeah, this is an addition reaction, electrophilic addition. And for reaction 2, you're adding potassium hydroxide to an halogenoalkane, and the iodide ion is being replaced by the hydroxide from the potassium hydroxide. So this is most likely a nucleophilic substitution. It's not elimination because elimination requires ethanolic um, ethanolic potassium hydroxide or NaOH. So I think it's B.
Yeah, like in addition, usually like if you look at the equation and you're just getting one product from two products, there's probably going to be addition, right? So you're just combining those products. So yeah, and then yeah, it's substitution as well, the last one for OH. So you're substituting the I for OH. You can see that from the equation that this iodine atom is getting substituted for the OH. So yeah, you just have to look at the equation basically. Yeah. And now next question. Okay. So an organic molecule W contains 3 carbon atoms. It requires 4.5 molecules of oxygen for complete combustion. So what could W be?
Contains 3 carbon atoms. So firstly, it has three. I think all of these are possible because prop, and it requires 4.5 moles of oxygen for complete combustion. I could just combust each of them separately, I guess.
Yeah, we could write the
C3H8,
equations for each of them.
yeah, plus O2. Mm, 2, 8, 5, C double H plus O2. H5, C double O. Mm, and lastly, C2H5OH plus O2. Okay, just a complete combustion, so all of them will produce carbon dioxide plus water. For this one, and it's 3 carbons, so all of them will produce 3 moles of carbon dioxide. Lastly, to balance the hydrogen atoms, there is eight hydrogen here, so four, six here, so three, um, six here, three, and six here, so three. Finally, to balance the oxygen,
I think the last one it's propane one ol, right? So yeah,
mm,
there should be more
uh,
hydrogens there. It's C3 it should be.
why?
Yeah, no, because they're not just six hydrogens, right? It's CH3, CH2, CH2OH, so then that would be C3H7OH, right?
Oh, right.
Yeah,
Yes. Okay, so four for this as well.
yeah,
I actually got confused because the rest of them, yeah.
yeah.
Um, so now six and four, you need um, there's 10 here and one, two, so you need nine, and to get nine, yeah, it's probably D, last one, but let me check the other ones as well. Six and three, you need eight, so four, six and three, you need seven to balance, so seven by two. And finally, this one, six and four, you need five. Yeah, the only one with 4.5 moles of oxygen is the last one, the 110.
Yeah. So yeah, we just balance the equation, write the equation for each one and balance it. C3H8 it has no other oxygen, so you have to just see that like C2H5COH already has two oxygens. So how many more do you need to add and stuff? So you just balance it. And we get the answer is D. Okay, next question now. Compound J C15H23Br2Cl is reacted with an excess of a hot concentrated solution of sodium hydroxide and ethanol. One of the products is X. So what could be the skeletal formula of X? So yeah, all of your elimination products, right? So that's nice. So hot concentrated solution of sodium hydroxide and ethanol must be a higher temperature and stuff. So you get elimination products.
For elimination products, we get like for this one, we can either remove this or this. I mean, I'm writing the possible double bonds that can form this or this and
Yeah, but that's not really a
this.
double bond, is it?
Mm,
This one. Those are just lines to show that they're substituents, like they're attached, right?
yeah, I mean, yeah, but I mean, like, I'm trying to draw a double bond.
Oh, sorry.
Yeah, okay. So I can check. Um, I can check with this. This can be possible, I guess. And this,
Yeah, so in
oh
this
wait,
reaction, you would get
no,
chlorine, like chlorine atom
no,
eliminated, and then from the carbon that's adjacent to it, you would also lose hydrogen, right?
Hmm.
So then,
Oh, yeah,
yeah,
right.
that's what's happening.
Hmm.
And so you would lose this. So you can't really form a bond there
Oh, yeah.
because
Oh,
yeah, the
sorry.
bond will be
Yeah.
formed between carbon
The
atoms,
bond
right?
only in the carbon. Hmm.
Yeah. But then we lose this chlorine and we lose hydrogen from the adjacent molecules. We could have a
Hmm.
double bond here, for example. And then yeah, we could also have one if we lose this chlorine and then we lose the hydrogen from this carbon atom, we could also have a double
Hmm.
bond here, possibly.
Yeah.
And we just have to look at that. I mean, it might be a bit messy, I
Hmm.
guess. But
And for B,
for bromine as
this,
well, we have to see.
hmm, this, and this. I think B is a possible answer. For the other ones, there is no double bond for chlorine here,
Yeah,
and for D as well, there's no double bond for chlorine. These two are eliminated. And A is not the answer because you need a hydrogen. Like, not that.
so could you repeat why A is not the answer?
The number of carbon atoms don't match.
Do they not?
No, there's one extra here.
Hmm. So that's why they didn't draw it because then you would have five
Yeah,
bonds. That's they just removed a methyl group for no reason. That's what you're saying.
yeah.
Yeah, that makes sense. So we can
So
eliminate
B is the
A.
only possible answer.
Yeah, so then for chlorine and bromine, like you have to form a double bond for each of them, and for this bromine atom as well. So you should have three double bonds added to your structure, but then in C you only have two, in D you only have two. In A they randomly removed a methyl group, so then yeah, D has to be the answer. If you cancel that, then it's losing edge from this atom, from this carbon atom, so you get double bond there. And for this like bromine's elimination, you get that removed and the hydrogen from this carbon atom, so you get a double bond here. And then yeah, for that one they removed. So okay. Yeah, I mean that's also I think another reason why this is not possible because you can't get a double bond in that position, right? Because
Mm.
you this carbon, it already has four groups attached to it, right?
Mhm.
So then it does not have any hydrogen. So then like if this bromine gets eliminated, it can't really eliminate a hydrogen from this place because there is no hydrogen on that carbon atom. So you can't get a double bond
Yeah.
over here. You cannot get a double bond there. So it's only possible for the double bond to be here then, right?
Yeah.
Yeah, so then I guess that's another reason why C is also wrong then. But
Okay.
then yeah, the answer has to be B. So you have double bond here and here and here. Yeah, it's good to check if in any structures like the elimination that they're carrying out, does it mean that carbon will have five bonds? And that's not possible, right? So
Mm.
okay, next question.
Okay. Number 26.
Yeah.
1 mole of compound Y reacts with sodium to produce 1 mole of hydrogen. So it's either alcohol or acid. Mm. I I guess I need to make the equation for this again. It's not this because this is an aldehyde. So it's either A, C, or D. For A, C4.
Is it an aldehyde?
Hmm?
Because usually for aldehydes,
Isn't
like
D an aldehyde?
I've always seen them write CHO whenever it's an aldehyde, not COH. So I'm not sure.
What is that then? It's not an acid or
You could
alcohol.
you could draw
Oh,
it,
right,
but
it's an alcohol. Okay, my bad. Right.
yeah,
I don't know why I thought that as an aldehyde.
I mean it's kind of confusing because sometimes CHO and then if they write COH, it just looks weird. But then yeah, it's useful to draw it
I'll
maybe.
check the equation now. C4 H9 OH plus NN. Then for B, yeah, C4H9 OH again. For C, C3 H7 CWH. And for D, C3 H. I guess I will draw it like this. H. By adding sodium to them, hydrogen is being produced and the carboxylate ion. So in this case, C4H9 ONA. Here C4H7 proporo Na plus H2.
That should be C3, right?
Why? C. I moved the carbon here to this side. This one.
Acha.
And the last one, C3. Okay, this can either react with the alcohol or the acid.
Or it could react with both of them.
But it's not said in excess. And even if it does,
Because the
uh,
thing is that the question says that, yeah, so basically like sodium can react with any OH group, right? Like even if it's
yeah,
in alcohol or if it's in the carboxylic
mm,
acid, like it can react with
mm,
both of them. Whereas like NaOH, that would only react with the OH in the carboxylic acid group.
mm,
So that's different. So then this like sodium, it can react with this like it can basically replace this hydrogen
mm,
of the alcohol OH and also this hydrogen and over here this hydrogen. But then if you have
mm,
CH3, CH, OH, CO2H, Why can't it be that it can replace both of the hydrogens, like even this one and that one?
Yeah.
Yeah.
No, normally if it reacts with what is written excess sodium or something.
Yeah. But then that's kind of the question.
Yeah.
Like it reacts with 1 mole of compound Y to produce 1 mole of H2, right? Like if you think about it,
Yeah.
then over here C4H9OH, like the first one, plus Na gives you C4H9ONA. But then it's not going to be H2, right? Because you're just replacing one hydrogen. So then to balance it, it should be 1/2 H2.
Yeah. Yeah.
You get what I'm saying?
Yeah. For C, it's the same.
Yeah, in C it will be the same. And then in B as well, because you're only replacing one hydrogen atom, right?
And for D, C, H6, O2, O3, Na2 plus H2. And for this, you can check if the equation is balanced. C3, H6, O3, Na2,
Plus H2.
H.
Because you're replacing two
Yeah.
hydrogen atoms, so you're losing
Hmm.
1 full mole of H2, right? So that's the question. Like
Yeah.
sodium reacts with 1 mole of
Yeah.
compound Y. We took 1 mole in all of them
Hmm.
to produce 1 mole of H2. But then the first one, because only one hydrogen atom is being replaced, it's 1/2 H2. Here as well, if you can like
Yeah.
write the formula. So then
It's the
that
same
hydrogen,
here, right?
yeah.
Same as A.
Yeah, I mean technically yes. If you look at the molecular formula of itself, then yes,
Hmm.
that technically is not molecular formula, but anyways. Na plus 1/2 H2. So then, yeah, because in D you have two hydrogen atoms being replaced, so that's the only one that will, like, if you're just considering 1 mole, then D is the only one that will produce 1 mole of H2 according to the equation. So yeah. So does that make sense?
Yeah, it does.
Good. So now we'll go to the next question. So which compound shows optical isomerism and gives a positive test with alkaline aqueous iodine?
Optical isomerism, we need a chiral center for this.
I think the meeting is about to end, so we should probably start a new one.
Okay, so number 27, right? Optical isomerism needs a chiral center. And for a positive test with alkaline aqueous iodine, we need uh, methyl ketone or alcohol.
Yeah, like the secondary alcohol.
Yeah, with methyl group attached to it. Yeah, so the first one, drawing the skeletal formula, a ketone, so double one here. And yeah, that's it. So this is an alcohol with a methyl group attached to it. There is possible. And for B, skeletal formula will be in another ketone. So, this is not a methyl ketone. There is an ethyl group here, and this ethyl group here as well, and no methyl group attached to the OH. It's not B.
Yeah.
And for
So
C,
the carbon chain should be a bit shorter. So like it said CH3CO CH2, right? So it should, this is CO,
oh,
then you just have CH3. This would be CH2
oh,
CH3, right?
oh, yes,
Yeah. Yeah, and so with alkaline aqueous iodine, the main group we're looking for is basically RCO CH3. So that's what a methyl ketone would have. That's what a secondary alcohol
mm,
has.
yeah.
So,
So A does have it.
yeah, then A would have that group, right?
Mm,
Here.
yeah. The answer should be A, but I'll check the other ones. This is B, not possible since there is no optical center. Yeah, there is no optical center. There will be hydrogen here. For C, there is an oxygen hydroxyl group here and two another hydroxyl group here in the methyl group. And for D,
Again, there's one extra carbon there.
hmm,
Yeah, like the
oh,
structure should be HO,
hmm,
CH2, CH, CH3, and then yeah, the CHO.
okay,
And this is
for
CHO, right?
D,
So this is the, it's not going to be an OH.
oh, yeah,
Yeah, so this is going to be the structure. Yeah.
yes, for D, two methyl groups, carbon, another carbon, OH here, and double O, it's an aldehyde.
Yeah. So yeah, in
Right,
general,
okay.
aldehydes do not give the
Yeah,
positive test
so
with alkyl icosahexaene, but then there is one
clearly,
exception. That's like ethanol, because
mm,
ethanol it looks like that, right? Like it's yeah, CH3, CHO. So then
yeah,
technically it does have RCOCH3 group, like you can yeah, have an
mm,
H there if you want to draw it, then you do have that group. And then
so the
similarly also
answer is A.
ethanol. Yeah, so the answer is going to be A. So you do have an this chiral
Chiral
center,
center.
and then
Yeah,
you also have this alkaline aqueous, like
yeah,
it will give a positive test with alkaline aqueous iodine, but then B,
mm,
it has no chiral center, even though it does give a positive test with alkaline aqueous iodine,
yeah,
because it has RCO, C double bond O, CH3. And yeah, C again, it does not give a positive test with alkaline aqueous iodine, right?
yeah. It's an alcohol without
Yeah.
ethyl ethanol.
Yeah, I mean, it's also like just a primary alcohol, so that obviously
Yeah,
if you have RCOCH3, that would have like R group and you have CH3, so that would
mm,
be a secondary alcohol. So that makes it easier to see also. Even though you do have a chiral center here, right? So yeah.
yeah,
And then there Yeah, again, you just have a tertiary alcohol, so that doesn't make sense. Like to
Yeah.
have to give a positive test with alkaline icosahexaene, so we can also eliminate that option. And so yeah, the answer is going to be A. And we go to the next question. Ethane dioic acid HO2CCO2H is reduced using an excess of lithium aluminium hydride LiAlH4. So that's quite a strong reducing agent. What is the organic product of the reaction?
So firstly, contact acid, something like this. Right. Um, when an acid is reduced, it is either an alcohol or aldehyde. Since this is, yeah, it's either an alcohol or aldehyde.
Yeah, but then lithium aluminium hydride is a really strong reducing agent, right? So
Yeah,
it'll
so it
just
should be directly taken to an alcohol.
yeah.
Uh, Only primary alcohols can be turned into acids, so it's a primary alcohol for sure. Ethanol, so obviously it's not methane. I'll check ethanol first. It's not ethanol because there's two post carboxylic groups, and both of them are going to be turned into primary alcohol. This is just hydrogen here. So it's not in.
Mhm.
And next for B, ethan diol, sorry, ethan 1,2 diol. So it's like this. Yeah, it gains 4 hydrogen atoms from there, and the it's also both of the carboxylic groups are turned into alcohols. So the answer is probably B, but let me check C as well. C, C, wait. Yeah, this is not the answer because there is no um, hydrogen atom here. It's probably a triple bond here, which is not possible in this case.
So the structure for C is they made ethane dial, right? So that's you have an
Yeah.
aldehyde on both sides.
Oh, yeah.
So it would be like CO double bond, and then you have
Oh,
H
mm.
like that.
Yeah, so this is not possible since lithium aluminum hydride is in excess and it's a strong reducing agent.
Yeah, so it's a strong reducing agent, so it will just immediately go to ethanol
Mm.
rather than going to the aldehydes. So that's how you can eliminate C as well. So then yeah, the answer is going to be B. So
Yeah,
the carboxylic acids just get reduced to primary alcohols. So then you can just add an OH group, and then also on the other side an OH group, and then just fill in because carbon makes four bonds, right? So the other two must be hydrogen for each one, and then yeah, you get ethane 1,2-diol. So yeah, and now the next question. The diester shown can be hydrolyzed by heating with an excess of aqueous sodium hydroxide. What would the products of this reaction be?
firstly, when a diester is hydrolyzed by sodium hydroxide, It produces the acid salt
Yeah, because
and
it's basic conditions. So
NHC. Yeah. Okay, so in this case, uh, it's not the ones that have acid salts are C and D. A does not have an acid salt. C, B, C, and D. Yeah. Wait, it's not. Uh, okay, that's possible too.
maybe it's easier if, instead of looking at the options first, to just look at how the
Yeah,
bonds would break and draw it, right?
yeah.
Yeah, so it would break there.
Just one and the other one. And lastly, there's the acidic part of it. This will be filled by hydrogen, should be,
Yeah.
and the acid reacts with the sodium. Yeah, so the answer is C. You can see that our hydrolysis matches with C.
Yeah, so
Yeah,
then because yeah, so because it's basic conditions, so wherever you have COOH, then yeah, it will just become the hydrogen will get replaced with sodium from sodium hydroxide because it's basic conditions, right? So the acid will get neutralized, so then it's just going to become COONA.
yeah,
And this product in the middle, like it's just you get OH there and OH there, but then that's an alcohol, so it won't be um changed by the basic conditions. It'll just remain OH and OH, but then HCOOH, which you get from here. So yeah, that would become HCOONA. So then yeah, it's either going to be C or D. And then
yeah.
on this
Or
side as well,
this
yeah,
one.
you get COOH over here, right? And then that OH gets replaced with sodium. So then yeah, we have NaO and this one, but then indeed they replaced the OH of the alcohol as well, which shouldn't be the case because it's sodium hydroxide, right? It's not sodium. Sodium is stronger as a base, so it can replace OH. Or it can replace the hydrogen of the alcohol as well, but then sodium hydroxide can't do that. So that wouldn't get replaced. So it should just be C. Yeah. Then the next question. J is a branch chain alcohol C5H12O. J is heated under reflux with an excess of Cr2O72 minus H plus until no further reaction occurs. An organic compound K is formed in good yield, and the infrared spectrum of K is shown. So, what are the structures of the branch chain alcohol J and compound K?
Wait, am I supposed to get something for this?
I mean, like the values, right?
Yeah, I don't think we're supposed to memorize that.
Yeah, no, you're not. You get them in the exam.
Oh, yeah, that's
Mm. But then,
Okay,
yeah,
so the sh- sharpest drop is here, which is around 1600, 1730 approximately, something like that. And the other, this is in the range of, even though this doesn't matter here, 1000 to
yeah,
1500. And the other sharp changes in 3000. Can you show
this
me the table?
this is the infrared spectrum of Kate's. There are no broad peaks over here, right? Usually, if there's
Yeah.
an alcohol, there would be a broad peak over there. So,
Hmm.
yeah, but then the options don't have a broad. Yeah, they have COH. So I guess you could kind of eliminate that.
Yeah.
But then, yeah, we can look at the.
Okay. 1730. It should be something with this group and
Yeah,
carbonium or ester. And the other, yeah, I don't think there's any other possibility.
yeah, because I mean, I don't know. This data booklet is for 2022 to 2024, but then I have the
It
2019 one,
shouldn't
so
change
that
too
has,
much.
yeah. I mean, even though we got a peak at 3000, that's usually like if it's for OH, that's a broad peak, right? So it looks
Yeah.
wider,
Mhm.
which I thought they would write here, but yeah, I guess now they don't. So yeah,
Mention. Mm.
that might just be like alkane or something then,
Yeah.
simply. And yeah, 1000 to 1500 usually most molecules have that, so that's not really, that's like fingerprint region
Yeah.
over there.
Okay.
They're not
So,
very short peaks.
um,
So yeah, then we
yeah,
can,
so I'm assuming this doesn't matter for now.
yeah, it might not. I mean,
Yeah.
or no, it could just be CH of alkane.
Yeah.
Okay, but then we can, because there's no broad peak for OH over here, so it can't be a carboxylic acid or an alcohol, so we can
Mm.
eliminate option D. Oh, why is it not letting me annotate? Okay, sure,
Mm.
that's fine.
Okay. Can you scroll a bit down?
Yeah,
Yeah. Okay. For C, yes. Okay. The infrared spectrum for K, right? Yeah, so C is possible. It has a ketonic group.
yeah,
B is also possible as it has a ketone group.
yeah. So we just need like
This as
which
well.
molecules have CO.
Yeah. And A as well. What else here is say J is heated under reflux. J is an alcohol that is heated under reflux of excess. So it's
Yeah, and
being
then
oxidized
yeah, so it must
and
be able to be oxidized. So then if you have like
yeah,
primary alcohols, secondary alcohols, tertiary alcohols
yeah,
can't be oxidized. So if there's a tertiary alcohol, we can't
yeah,
have that. So maybe there's something there.
yeah. For A, it's a primary alcohol and it's being oxidized to an aldehyde. Oh, it said excess of that, so it should be an acid, not an aldehyde. It's not A. For B, it's a um, it's a secondary alcohol And secondary alcohols are oxidized to ketones.
Yeah. So now we have a choice between B and C.
Yeah, B and C.
What else did they mention in the question?
Until now, northern found is found in between.
They also said it's a branched chain alcohol.
Oh, yeah, branched chain alcohol. Yes, B. This is not a branched chain alcohol. This is single chain. And so B is also cancelled. And lastly, for C, yeah, it's a branched chain. It will be something like this. For C, the structure Yeah, this is the structure for C, and it is a branched chain alcohol because there's methyl branch. Yeah, so the answer should be C.
Yeah, but then in B there's no branching, so that can't be it.
Yeah.
And then D, yeah, D we eliminated because in the spectrum there's no broad peak for OH, but then COH you would see a broad peak over here. And then yeah, A A as well because they said excess of Cr272 minus, so until no further reaction occurs. So there shouldn't be an aldehyde, it should already be like a carboxylic acid if A was the answer. And so we get
Yeah.
C.
C.
Yeah, okay, next question now. Question 31. So which ions contain one or more unpaired electrons? So you can go to the
So
data booklet as well.
yeah, we have Cu plus Mn3 plus and V3 plus. Okay.
Yeah.
For Cu2 plus, the electronic configuration will be Ar from 1. Being 9, 3D10, and 4S1. That's it.
Yeah, because you're going AR
18.
and then you have 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 9. But then the preferred thing is actually 3d10, 4s1.
Yeah, and then we remove 2 electrons from it.
Yeah, for the CO2 plus.
Yeah, so it's removed from 4S first.
Yeah, because it's the outer shells.
3D9. Yeah.
So you would have 3d9. So the question said which ions contain one or more unpaired electrons.
And then next for Mn, Ar 3D7.
Yeah, so 3d1, 2, 3, 4, 5.
Yeah, wait, 3D4.
We just use the periodic table for that, right?
Yeah.
Like we had the argon configuration and then you have 4s2 because this is the S block, right? So
Yeah.
4s2, and then this is the D block. So you have to see 3D1, 2, 3, 4, 5. So it should be 3D5 there.
Oh yeah. Right.
Yeah. 3D5 and 4s2.
Wait, no, like
You mean
I
when it's
lose
lost?
3 electrons.
Yeah. Yeah, then you're going to lose the 4s2, the 2 electrons from there, and then you're
Yeah.
going to lose one more. So that will become 3D4. Yeah.
Yeah, 4. And for V3 plus argon, then where is vanadium?
Yeah.
Yeah, 23. 3D3 4s2. So it should 3D2.
Yeah. So it's going to lose the 4s2 electrons, and then because it's V3 plus, right? So then it's going to lose 3
Yeah.
electrons first, the 4s2 ones, and then one more because this is 3D1, 2, 3. So it's going to lose one from there as well. So it's going to become 3D2. Okay. So now we have to see which one has one or more unpaired electrons.
Can you move to the question?
Yeah.
Okay. For the first one, we have there is only one unpaired electron in the D shell, the orbital. There is only one unpaired electron.
Yeah. So you have 1, 2, 3, 4, 5, and 6, 7, 8,
And for
9. So there's one unpaired
the
electron.
V3 plus, we have two unpaired electrons. And lastly, for Mn3,
For Mn3 plus, it's 3D4, right?
this is V3 plus, by the way. Um, this is
Oh, okay.
this is Mn.
Yeah, V3 plus. We have 2 electrons.
So for Mn, there's 4. So yeah, the answer is A, as A means all 3 of them.
Yeah, so in Cu2 plus we have at least one unpaired electron, then V3 plus we have 2, and then Mn we have, in 3 plus we have 1, 2, 3, 4. So then all of them have unpaired electrons. So then the answer is going to, yeah, the answer is going to be, yes, A means 1, 2, and 3 correct, B means 1 and 2 are correct, C 2 and 3 correct. Great. So question 32. Which molecules and ions have a bond angle of 120 degrees?
BS3, BS boron does not have a lone pair, so it does have 120 degree. And next, CH3. It's a negative ion, so it must have a lone pair somewhere. So this is not 120, this is 109 degree. It, is it? No, it's 107 degree. Yeah.
Yeah,
So
because the lone pair will reduce the bond angle a bit, so it's going to be
yeah,
107 degrees.
107. Okay, the last one, NH3. This is also 107 as there's a lone pair here.
Yeah.
It's a pyramidal structure.
Yeah, this
So the
one as well.
only, yeah, these two are same. So the only possible answer is A. The answer is D.
Yeah, because only one is correct.
Yeah,
So yeah, you
one.
just have to look at Westward theory.
Mm,
And so yeah, over here you like boron, you have like one, two, three bonds and then no lone pairs. So that's going to be sp2, and then that's going to be 120 degrees. And here one, two, three bonds and then one lone pair. So your steric number, which means your number of um bonds that you have, are like not really bonds, but only like sigma bonds. Like you only count it once, plus the number of lone pairs you have on the carbon on the atom that you're looking at, like the atom that's forming the bond angle. So then yeah, you're gonna one, two, three, four. So that's going to be sp3, but then which usually has 109.5, but then because of the lone pair, it's going to be 107. And then the same for ammonia.
yeah.
So then yeah, the answer is going to be D, because only one is correct. Okay, now next question. Which statements are correct for all exothermic reactions? So what are the options? Delta H for the reaction is negative. On a reaction pathway diagram, the products are shown lower than the reactants, and then the reaction will occur without heating.
For all exothermic reactions. Actually, I'm pretty sure 3 is wrong because um, exothermic reactions in general require heating.
Yeah. Like you need some heat to initiate the reaction, but then after that it can
Yeah.
maybe continue
Mm.
spontaneously, but then I have to
Okay,
you
then
sometimes need to provide heat. So yeah.
on reaction pathway diagram, the products are shown lower than before the exothermic reaction. This is the reaction pathway diagram, and yeah, products are shown lower than reactants. This is right.
Yeah.
Del H is negative. Yeah, the del H is always negative for exothermic. So the answer is B, as 1 and 2 are correct.
Yeah, so I mean, option one and two here are related as well, because if you draw the reaction pathway diagram, you can see that the arrow is downwards, so it's delta H is negative, and then yeah, reactants are higher and products are lower. So yeah, but then the reaction will occur without heating. That's not necessary, because you might need heat to initiate it. And so we go to the next question. Yeah. The factors affecting the rate of reaction between aqueous sodium thiosulfate and hydrochloric acid can be investigated. So the ionic equation for the reaction is shown. So you have S2O32 minus thiosulfate ion plus 2H plus, giving you H2O plus S solid plus SO2 aqueous. So that's actually like that disappearing cross experiment that's kind of famous
Mm,
in like labs and stuff. So yeah.
mhm.
Now, which of the following can be used to investigate the rate of this reaction? Change of mass, change of appearance caused by formation of a precipitate, but maybe even change of electrical conductivity. So yeah.
Mm. Okay, firstly, change of mass. The mass does not change, does it? Because there is no gas here. This is aqueous SO2. So one is out of the case. Change in appearance caused by formation of a precipitate. Yeah, there is sulfur forming, which is a yellow precipitate.
Yeah.
So as we all know, this reaction produces color precipitate. So yeah, this is possible. And change of electrical conductivity. Yeah, firstly, there's ions here, and there are no ions here. So this would not conduct, and the left hand side of the reaction would conduct. So 2 and 3 are, there is a change in electrical conductivity. So 2 and 3 are correct. The answer should be C.
Yeah. Then yeah, obviously you can't really measure the change of mass that much because a gas is not liberated.
Yeah, yeah,
But then yeah, you do have an ionic difference. You have ions here, you don't have ions there. But then sometimes like you can have,
mm,
okay, yeah, so the Zoom meeting ended, but anyways, the point is that yeah, sometimes you can have ions on both sides, but then there's still an ionic difference because you have more ions or less ions or like stronger ionic conductivity and
yeah.
less strong and stuff. But then yeah, the answer is going to be C. So next question. Which reaction routes can be used to make a pure sample of barium sulfate? Okay,
Okay,
so
so
see.
barium metal heated in oxygen. So BaO, BaO, and there is being BaO plus HCl. And, yeah, BSCl, something BSCl2 plus water. Okay. And BSCl2 plus H2SO4 gives us a white precipitate of BSO4.
Yeah, so for BaCl2, we won't get a precipitate because all chlorides are soluble, right? So that's
Yeah,
just going to be
yeah.
BaCl2.
Mhm.
But then
And
sulfate,
yeah,
like
so
yeah, group two sulfates,
the sulfate ion. Yeah.
yeah. So like you have group two, right? So then the solubility of the sulfates decreases down the group.
Mm,
So
mm,
that's why we get barium sulfate
mm.
solid.
And the next is piano 3 heated in strong air. It would also produce BaO as the nitrate is being thermally decomposed. And then in excess of water, uh, it does not dissolve in excess water, does it?
Yeah, I mean you have to think about group two hydroxides, right?
Oh, all right. Yeah.
How would
It
their
turns into a
solubility be?
yeah, it turns into a hydroxide, so
Yeah.
PaOH2. And lastly, when you add PaOH2 aqueous to H2SO4, it does form BaSO4.
Yeah. Then yeah, you got
Okay. Yeah.
BaOH twice here, but then BaOH twice aqueous. That is
Mm-hmm.
soluble. It's in water, so it's not a precipitate because group two
Mm-hmm.
hydroxides their solubility increases down the group. That's
Yeah.
that's more of an like the logic behind that is more A2, but yeah, you
Yeah.
should kind of know it still. And then yeah, BaSO4 is a solid, so you can then yeah filter it, you can wash it and dry it.
Mm.
So that's why.
And the last one, barium hydroxide plus dilute HNO3. So it's an acid-base reaction producing BNO3. And this is aqueous as all nitrates are soluble. And adding this to H2SO4 will give us BaSO4.
It's, it's going to be BaNO3 twice, right? Because NO3
Oh yeah,
minus that
yeah,
has, yeah.
yeah. Okay. So yeah, all of them. It's A.
Yeah, so all of them, you can use them to make barium sulfate precipitate or barium sulfate solid. So yeah, then that's just going to be A. Now, next question. Which properties increase from magnesium to barium? Ionic radius of the cation M2 plus, screening of outermost electrons by inner shells, solubility of the hydroxides, MOH twice in water. I'm just going to write down group 2
So
here.
mm, from magnesium to barium, it's down the group. So
Yeah,
atomic radius always increases down the group.
yeah, and then similarly, ionic radius will also increase then.
Yeah,
So
consequently, yeah. So A is right. And then screening of outermost electrons by inertial. Isn't that shielding? It,
this is the same
yes,
thing. Like
yeah,
it's
same.
yeah, we like it's like there's a constant associated with it, which is called a screening constant. So
Oh,
it's called a screening constant.
mhm.
So it should be fine.
So as the atomic radius increases, the number of inner shells also increase. So more inner shells repel the outer shell, and that makes screening, and that increases screening of outermost electrons by inner shells. So, yeah, that's also right. And then there's solubility of the hydroxide. We just did that a few minutes ago, that solubility of hydroxide increases for hydroxides of group 2, and magnesium to barium is group 2. So this is also right.
Yeah.
So the answer is A.
Yeah, so all three of them are correct. And yeah, screening of
Yeah.
outermost electrons by inner shells increases because the number of inner shells increases, right? So yeah. And now we go to the next question. So 2-methylpropene can react in more than one way with chlorine. One of the reactions follows the pathway shown. So which statements about this mechanism are correct?
Okay, so first one, the intermediate has all carbon atoms in the same plane. This is the intermediate. Does it have all carbon atoms in the same plane? For this carbon, it's like this. So this is a tetrahedral structure.
But then there is a plus charge, right? And
Mm,
or earlier as just talking about carbon in general.
yeah. And for this carbon, it's the same tetrahedral again. For this one,
Okay, you're looking at each of the carbons here.
yeah. And yeah, this is also a tetrahedral structure. And lastly, the carbon in the middle. Yeah, we could just look at that. Yeah. There are three here and a positive charge. That makes a 120-degree, right?
Yeah,
Yeah,
because there's one, two, three bonds and no lone pair,
yeah,
so that's going to be
yeah.
sp2. So it's
Hmm.
120 degrees.
So yeah, all of its carbon atoms are in the same plane. This is a planar structure. trigonal planar.
Yeah, so trigonal planar means like, yeah, basically
Yeah,
it's a
or
flat molecule like that. Like
mm,
I mean, not a flat because then you have to, yeah, these other carbon atoms, they're tetrahedral, so it would not, they would not,
yeah,
those their atoms would not lie on the same plane,
mm,
but then the carbon atoms, all of them lie on the same plane, right?
yeah. Yeah.
Because
So
yeah,
yeah,
so
one is right.
this
There
has
is an
trigonal planar,
mm, mm.
so all of these are on the same plane. Yeah,
Then there is an electrophilic attack on the double bond. This is an electrophilic addition reaction. Yeah. So this happens in the double bond so that the double bond breaks by an electrophilic attack. So yeah, two is right. And it is
yeah,
a free radical mechanism. No, it's not a free radical
it's going to
mechanism.
attack.
Yeah,
And I mean, technically, yeah.
mm, it's not a free radical mechanism. It's electrophilic addition, and there are no free radicals involved. So yeah, it's one and two. B.
Yeah, that seems right. Yeah, because obviously you can't see any free radicals. So.
Mm,
And next question. The halogenoalkanes listed below all react with NaOH aqueous, which reactions proceed mainly by an SN1 mechanism. So we have 1 iodopropane, 2 iodo, 2 methylpropane, and 2 bromo, 2 methylbutane.
Okay, so SN1 mechanism is only for tertiary um, tertiary halogen
Yeah, usually because they have more steric hindrance, right? Like they have three groups, so it's harder for
Yeah,
it to be substituted using
yeah,
SN2.
stronger positive inductive strength, more stable. So firstly, for one iodopropane, eh, for one iodopropane, it's something like this. This is the primary halogen alkane. So it goes by the SN2 mechanism. One is eliminated. The answer is C, as the only other options are 2 and 3. But I'll check them as well. C, this is for C, number 2. 2 iodomethane. There's here. Yeah, this is a tertiary halogen alkane, as you know, there's 3 alkyl groups attached to it. And for number 3, 2 bromo 2 methyl butane. Yeah, so this is also um, a tertiary halogen alkane. There's 3 alkyl groups attached to a carbon with the halogen. So the answer is C.
Yeah, yeah, because the first one was primary, so that would prefer SN2, but then the other two are tertiary, so they prefer SN1 because of steric
Mm,
hindrance. So question 39. 3-oxobutanoic acid can be synthesized in a two-step process. What could be the structure of X? So we have to kind of just predict it.
yeah. It can be synthesized in a two-step process. So the only possibility is that this is a primary well, I mean, one of the possibilities is that it's a primary alcohol.
We could use the structures that they've given and see how we can reach 3-oxobutene.
Okay, firstly, this works. I think one is right because it has a primary alcohol. And then this is uh, an acid with with a halogen with it. Two-step mechanism. You replace the chlorine atom with oxygen.
It is a 2-step mechanism, so you could do it in 2 steps.
Yeah.
So first you could replace it with OH, using nucleophilic substitution, and then you could, oxidize the secondary alcohol,
Oh, yeah.
right?
Right. Hmm.
That could be the
Yeah.
thing. You would get OH, then you would get
oxidize to this.
then we could oxidize it using like K2Cr2O7 or something.
Yeah, so use also it.
There we could use NaOH.
Yeah. And lastly, 3 is the same as 2, right?
Yeah, I mean the compound is different because you have bromine, you have aldehyde.
In case of the final step of oxidation would be the same.
And we could draw the mechanism and see.
Yeah. Okay. NaOH first to remove the BH2. Then oxidized by something like this. Get to Cr2O7.
Yeah, potassium dichromate, acidified.
Yeah, acidified potassium dichromate. Then yeah, it would be the same. So 3 is also right.
Yeah. Then could you also draw the mechanism for 1 then?
Mechanism for 1. Firstly, we break the double bond form using H2O because steam.
Yeah.
Forming this. Then acidified potassium dichromate. You get the same structure. Yeah, that's it.
Yeah. So then 1, 2, and 3, they're all possible,
The
like
answer is
2-step
A.
process. Yeah, so then the answer will be A. And now is the last question, right? So ethanol reacts with HCN in the presence of KCN. Which changes in bonding occur during this reaction? So a
This
carbon-carbon
is
bond, hydrogen-carbon, or nitro. Yeah, we could just draw the mechanism or something.
hmm, This is a nucleophilic addition reaction. Okay, so firstly we have ethanol. Then the double bond here in oxygen is being broken. It's a CN minus ion.
Yeah, so you have to be very. I don't know how hard it is to draw on the computer, but then like your arrows have to be very precise. So then the double bond is broken, so you should go from the bond to the oxygen.
Yeah, yeah. Then the intermediate forms. Mhm. The last step.
And then now you're going to have an extra lone pair over there. So before, like, obviously oxygen has two lone
Right,
pairs.
yeah.
And then now you have three. So there's a minus charge there now. Because obviously, in a reaction, your charge is conserved and also the 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 balance the equations, right? So the mass kind of stuff. But um yeah, then the next step, you're going to have HCN.
HCN.
The bond there.
The lone pair attacks this and
Hydrogen.
HCN breaks.
Yeah, right from the bond to carbon.
Yeah. So the final compound is formed. Yeah. Okay, now I can check for them. A carbon-carbon bond is formed. Yeah, wait, I think I must have now, since the lone pair is given by the carbon here, the carbon-carbon bond is formed.
Yeah, like this.
So one is right. Yeah. Then a carbon-hydrogen bond is broken. Yeah, here in HCN, a carbon-hydrogen bond is also broken. And lastly, a carbon-nitrogen bond is formed. Now, the carbon-nitrogen bond is not formed as the bond formed is carbon-carbon here. So the answer is B.
There's no carbon-nitrogen bond broken or formed. Just have CN, but then that bond is not being broken. So yeah, then 1 and 2 are right. So the answer is going to be B.
Yeah.
Okay, now we are done. So that was fun, and yeah, it was a cool idea to do this collab. I guess initially it was a bit like it took some time to get used to it, but then later it became better. So that's good. Okay, so thank
I
you.
also got practice. Yeah, thank you too.
Yeah, it's good that you got practice actually.
Yeah.
Yeah. Maybe we could do this also some other time, but then now I don't have time, but like maybe later.
Yeah.
Okay.
Yeah, that's done. Bye.
Bye, guys.